as you settle in, allow the world outside to fade away. Let the sounds of your day soften into a distant murmur and bring your awareness to the gentle rhythm of your own breath. Tonight, we embark on a journey not across land or sea, but through the vast, silent expanse of the cosmos. We will travel to the very edges of understanding, to explore the quiet architecture of everything that is. Look up in your mind's eye at the deep, velvet blackness of a perfect night sky. It is a canvas dusted with the diamonds of distant suns, a view that has captivated humanity since our very beginning. We see the soft, milky river of our own galaxy, the Andromeda Galaxy, as a faint, ghostly smudge, and countless other points of light, each a star, each a potential sun to worlds unknown. This is the universe we know, the universe of light, of warmth, of matter that we can see and touch. But this brilliant, beautiful display is a grand illusion. Not an illusion in that it isn't real, but an illusion of completeness. For everything we see, every star, every galaxy, every nebula glowing with the fire of creation, all of it amounts to less than 5% of what truly exists. The rest, the overwhelming majority of the cosmos, is hidden. It is a universe of darkness, a silent, invisible ocean in which our islands of light are adrift. And within this ocean, a mysterious substance, an unseen presence, quietly shapes everything. It is the ghost in the machine of the cosmos, the invisible scaffolding upon which the grandest structures are built. We call it dark matter. It does not shine, it does not reflect light, it does not interact with us in any way we can directly perceive. Yet, its gravitational pull is the single most dominant force in the shaping of the universe on a grand scale. It is the silent puppeteer pulling the strings of galaxies, orchestrating their cosmic dance, and weaving the very fabric of the universe into a structure of unimaginable scale and beauty, the cosmic web. Our journey tonight is into this darkness, into this profound mystery. We will not be afraid of this darkness, for it is not an empty void. It is a substance, a fundamental component of our reality, and understanding it is to understand the true nature of our cosmic home. So relax, let your body grow heavy, and let your mind remain open as we drift into the story of the universe's invisible architecture. Our story begins not with a sudden discovery, but with a quiet, nagging puzzle, a loose thread in the grand tapestry of astrophysics. It began in the 1930s with a brilliant and famously cantankerous astronomer named Fritz Zwicky. Picture him, if you will, at the Mount Wilson Observatory, the cool night air of California, a stark contrast to the fiery, celestial objects he studied. Zwicky was observing a colossal structure known as the Coma Cluster, a congregation of over 1,000 galaxies bound together by their mutual gravity, like a swarm of celestial bees. He was attempting to weigh this entire cluster, a task of audacious scale. To do this, he used two different methods. First, he counted the galaxies and estimated their brightness, and from that, their total mass in stars. This gave him a number for all the luminous or visible matter in the cluster. But Zwicky had a second, more clever method. He observed the motion of the galaxies on the outer edges of the cluster. According to the laws of gravity, first laid down by Newton, the speed at which these outer galaxies orbit the center of the cluster depends directly on the total mass contained within that orbit. The more mass, the stronger the gravitational pull, and the faster the galaxies can move without flying off into space. When Zwicky measured their velocities, he found something deeply disturbing. The galaxies were moving at tremendous speeds, far faster than they should have been based on the amount of visible matter he had calculated. It was as if you were watching a merry-go-round spinning at the speed of a jet engine. The horses should have been torn from their posts and flung into the distance. These galaxies, according to all known physics, should have escaped the gentle gravitational embrace of their luminous siblings and dispersed into the void. Yet they remained. They were steadfast in their orbits, held in place by a gravitational force of immense strength. Zwicky's calculations showed that for the Coma cluster to remain gravitationally bound, there had to be at least 400 times more mass than what he could see, an enormous, unseen mass. He called this missing mass Dunkel Materie, or dark matter. For decades, Zwicky's discovery was largely ignored, treated as an anomaly, perhaps an error in his observations or a peculiarity of the Coma cluster. The astronomical community wasn't ready for such a radical idea. The universe was supposed to be made of the things we could see: stars, gas, and dust. The idea of a vast, invisible cosmos was too strange, too revolutionary. But the universe does not care for our expectations. The puzzles Zwicky had uncovered would not go away. It would lie dormant, a quiet whisper in the halls of astronomy, waiting for a new voice, a new set of eyes to confirm its profound implications. That confirmation would come decades later, not from a galaxy cluster, but from within individual galaxies themselves, through the patient and meticulous work of an astronomer named Vera Rubin. In the 1960s and 70s, Vera Rubin, alongside her colleague Kent Ford, was studying the rotation of spiral galaxies, our own Milky Way's beautiful cousins. Using powerful new spectrographs, she could measure the speed of stars at various distances from the galactic center. The expectation was simple, based on how our own solar system works. Planets closer to the Sun, like Mercury, orbit at incredible speeds, while planets further out, like Neptune, move much more slowly. This is because most of the mass of the solar system is concentrated in the center in the Sun. The gravitational pull weakens with distance, and so the orbital speeds decrease. Everyone expected to see the same pattern in galaxies. The stars near the bright, dense galactic center should be moving quickly, and the stars on the faint, outer edges should be moving much more slowly. But that is not what Vera Rubin found. Again and again, in galaxy after galaxy, she found something that defied all logic. The stars on the outer edges were moving just as fast as the stars near the center. This flat rotation curve was a stunning anomaly. It was as if Neptune were orbiting the Sun at the same speed as Mercury. The only way this could be possible is if the mass of the galaxy was not concentrated in the luminous center. There had to be a huge amount of unseen matter distributed throughout the galaxy, extending far beyond the visible edge of the stars. This matter formed a vast, spherical halo of immense mass, and the visible spiral disk was just a small, glittering component embedded within it. The stars on the outskirts, though they seemed to be at the edge of the galaxy, were actually still deep within this enormous halo of dark matter, feeling its powerful gravitational pull and thus maintaining their incredible speed. Vera Rubin's work provided undeniable, compelling evidence. Zwicky's Dunkel Materie was not a fluke. It was a fundamental component of every galaxy. The universe was indeed mostly dark. This invisible substance, this dark matter, wasn't just some exotic anomaly in a distant cluster. It was here, in our own galactic backyard, surrounding us, enveloping the Milky Way in its unseen embrace. The very stability of our home galaxy, the elegant spiral arms we so admire, is owed to this vast, invisible halo whose existence we can only infer. This realization was a profound moment of humility for science. It was the cosmological equivalent of an ancient map maker suddenly realizing that the continents they had so carefully charted were just small islands in a vast, unexplored ocean. The map of the cosmos had to be redrawn, with a new, invisible continent that was 5 times larger than all the known lands combined. But what is this stuff? Knowing it's there is one thing. Understanding its nature is another entirely. This is where the mystery deepens, where the journey takes us from the realm of observation into the realm of theoretical physics, a world of exotic particles and strange new possibilities. Scientists began to categorize what dark matter could not be. It couldn't be ordinary matter like dark clouds of gas or dust, because those would absorb and re-radiate light in the infrared spectrum, and we don't see that. It couldn't be made of dead stars or black holes, because we would be able to detect them through other means, such as gravitational microlensing events, in far greater numbers than we do. This led to the conclusion that dark matter must be something fundamentally different from the matter that makes up you, me, the Earth, and the stars. It must be a new kind of particle, one not included in the standard model of particle physics, which is our current, incredibly successful theory of all known particles and forces. This hypothetical particle would need to have some very specific properties. It must have mass because it exerts a gravitational force, but it must interact very, very weakly with ordinary matter and with light. It passes through us, through the Earth, through entire stars, as if we were not even here. It is a ghost, but a ghost with gravity. Physicists have proposed many candidates for what this dark matter particle could be. One of the leading ideas is a class of particles called WIMPs, which stand for weakly interacting massive particles. These are hypothetical particles that are heavy, perhaps hundreds of times more massive than a proton, and interact only through the weak nuclear force and gravity. They are a compelling candidate because certain theories of physics beyond the standard model, like supersymmetry, naturally predict the existence of such particles. In these theories, every known particle has a heavier superpartner. The lightest of these superpartners would be stable and would have all the right properties to be dark matter. If this theory is correct, then the universe is filled with a sea of these WIMPs, left over from the fiery chaos of the Big Bang. Another intriguing candidate is a much lighter particle called the axion. Axions are hypothetical particles originally proposed to solve a completely different problem in particle physics related to the strong nuclear force. It was later realized that if they exist, they would have been produced in enormous quantities in the early universe and would have the right properties to be dark matter. Unlike the heavy, solitary WIMPs, axions would be incredibly light and would form a vast, coherent wave flowing through the cosmos. The search for these particles is one of the most exciting frontiers in modern science. Deep underground, in former gold mines and road tunnels, scientists have built incredibly sensitive detectors, shielded from the constant rain of cosmic rays on the Earth's surface. Experiments with names like LUX Zeppelin, Xenon, and Panda X are essentially waiting in the dark, hoping to catch the faintest whisper of a dark matter particle bumping into one of the atoms in their detector. It is a search for a single, tiny vibration in a vat of purified liquid xenon, a signal so faint it is almost indistinguishable from background noise. These experiments are marvels of engineering, pushing the limits of technology to detect an interaction that may happen only a few times a year, if at all. But the evidence for dark matter is not confined to the motion of galaxies. There is another, perhaps even more elegant, line of evidence that comes from the way dark matter warps the very fabric of space-time itself. This phenomenon is called gravitational lensing. According to Einstein's theory of general relativity, mass curves space-time. Think of it like placing a heavy bowling ball on a stretched rubber sheet. The ball creates a dip, a curve in the sheet. Now, if you roll a small marble past the bowling ball, its path will be deflected by this curve. Light behaves in the same way. When light from a distant galaxy travels towards us, its path can be bent if it passes by a massive object like another galaxy or a galaxy cluster. This massive object acts as a cosmic lens, distorting and magnifying the light from the object behind it. We can observe this effect. We see images of distant galaxies stretched into arcs, smeared into rings, or even duplicated into multiple images. These beautiful, surreal distortions in the sky are direct visual evidence of space-time being warped. And here is the crucial part. When we calculate the amount of mass needed to create the lensing effects we observe, we once again find that the visible matter is not enough. The amount of gravitational lensing is so strong that it can only be explained if galaxy clusters are filled with vast amounts of dark matter. The dark matter, though invisible, betrays its presence by its gravitational influence on the light that passes through it. It allows us to create maps of where the dark matter is, even though we cannot see it directly. We can trace its distribution, revealing massive, clumpy halos of this invisible substance that perfectly align with the locations of galaxy clusters. It is like seeing the footprints of an invisible giant in the sand. You cannot see the giant, but the evidence of its weight and presence is undeniable. And perhaps the most powerful evidence of all comes from the very beginning of the universe, from the faint afterglow of the Big Bang, a sea of microwave radiation that permeates all of space, known as the cosmic microwave background, or CMB. This radiation is a snapshot of the universe when it was only about 380,000 years old. At that time, the universe was a hot, dense soup of particles and radiation. As it expanded and cooled, tiny fluctuations in density, small seeds of structure began to form. These fluctuations are visible today as minuscule temperature variations in the CMB. By studying the precise pattern of these hot and cold spots in the CMB, cosmologists can learn an incredible amount about the early universe, including its composition. And the data, collected with incredible precision by missions like the Planck satellite, tells a clear story. The patterns we see in the CMB can only be explained if the universe, even at that very early stage, was composed of about 27% dark matter and only 5% ordinary matter. The dark matter was essential for the formation of structure. Ordinary matter, the stuff of atoms, was pushed around by the intense radiation in the early universe, preventing it from clumping together easily. But dark matter, being immune to this radiation pressure, could begin to collapse under its own gravity much earlier. It formed deep gravitational wells, pockets of intense gravity. As the universe expanded and cooled, the ordinary matter could then fall into these pre-existing wells of dark matter, like water flowing into a deep valley. This is how the first stars and galaxies were formed. Without dark matter to provide this initial gravitational scaffolding, the universe would not have had enough time to form the large, complex structures we see today. The galaxies, the clusters, the great walls of galaxies stretching across millions of light years. None of it would exist. The universe would be a much more uniform, diffuse, and perhaps lifeless place. Dark matter is not just a passive component of the cosmos. It is the architect. It is the unseen force that sculpted the universe, that guided the formation of every galaxy, including our own. This brings us to the grandest scale of all, the large-scale structure of the universe. When we map the positions of millions of galaxies, a breathtaking pattern emerges. The galaxies are not distributed randomly throughout space. They are arranged in a vast, intricate network of filaments, walls, and clusters surrounding enormous, nearly empty regions called voids. This structure is known as the cosmic web. It is the universe's skeleton, its nervous system. And this entire magnificent structure is traced out by dark matter. Computer simulations, which are among the most complex calculations ever performed by humanity, show us how this structure evolved. Starting with a small fluctuation seen in the cosmic microwave background, these simulations model the gravitational pull of dark matter over billions of years. We can watch as the dark matter slowly collapses into a web-like structure. The dense filaments of the web are the superhighways of the cosmos, channeling matter towards the intersections, the nodes of the web. And it is in these nodes that the great galaxy clusters form, massive cities of light built at the crossroads of the invisible dark matter network. The visible galaxies are like foam on the waves of a dark ocean, or like glowing lights strung along an invisible cosmic filament. They are merely tracing the underlying dominant structure of the dark matter. So when you look at a deep field image from the Hubble Space Telescope, with its thousands of galaxies of all shapes and sizes, you're not just seeing a random scattering of light. You are seeing the brightest points of an immense, invisible structure, a cosmic architecture that fills all of space. Each galaxy is a testament to the gravitational power of a dark matter halo that it resides within. Each cluster of galaxies is a monument built on a foundation of dark matter. The silent, empty-looking voids between the galaxies are truly empty of both light and dark matter. Our journey into the dark has shown us a universe far stranger and more magnificent than we could have imagined. It has revealed that the beautiful, luminous world we see is just the tip of a cosmic iceberg. The vast majority of matter in our universe is a substance we do not understand, a particle we have not yet discovered. This mystery is not a failure of science, but its greatest triumph. It is a testament to our ability to infer the unseen, to understand the universe not just through what we see, but through the subtle, powerful language of gravity. The quest to identify the dark matter particle is a journey to understand our fundamental makeup, to complete our inventory of the cosmos. As you continue to relax, to drift deeper into a state of peace and tranquility, let your mind ponder this invisible universe. Imagine these vast, silent halos of dark matter cradling each galaxy. Picture the immense, glowing filaments of the cosmic web stretching across unimaginable distances, a silent, invisible network connecting everything. There's a quiet majesty in this hidden architecture. It reminds us that the universe is not just what we see, but also what we don't. That the most powerful forces can be the most subtle, and that the greatest mysteries often lie hidden in plain sight in the darkness between the stars. The very ground beneath you, the air you breathe, your own body is constantly being pierced by a gentle, ceaseless rain of these dark matter particles flowing through the universe, through our galaxy, through our world, completely unnoticed. They are a silent, constant companion on our journey through space. Their presence is a quiet hum beneath the symphony of light and life, a foundational note that holds the entire cosmic composition together. The search for its identity continues, a patient global effort. Perhaps one day, a tiny, anomalous flash in a detector deep underground will signal the discovery of a WIMP. Or perhaps a subtle oscillation in a powerful magnetic field will reveal the presence of the elusive axion. Or maybe the answer will be something else entirely, something even more strange and wonderful than we have yet conceived. Whatever the answer may be, Its discovery will mark a new era in our understanding of the cosmos, a moment when the dark universe finally begins to give up its secrets. But for now, it remains a profound and beautiful mystery, a testament to the infinite complexity and wonder of the universe. It is a reminder that there is always more to discover, always a deeper layer of reality to explore. And as you drift towards sleep, you can rest in the knowledge that you are part of this grand, mysterious cosmos. You are held by the gravity of the Earth, which is held by the gravity of the Sun, which is held in its orbit within the Milky Way by the immense, invisible embrace of a dark matter halo. You are part of a structure so vast, so intricate, so silently beautiful that it almost defies comprehension. Allow this sense of connection, this sense of wonder, to be your final thought as you let go completely. Let the mystery of the dark universe cradle you, just as it cradles the galaxies, as you drift into a deep and peaceful sleep. The story of dark matter is a story of gravity's triumph over light. In our everyday experience, light is everything. It reveals the world to us. But on a cosmic scale, gravity is the true master. And most of the universe's gravity comes from a source that is completely dark. This has profound implications for the ultimate fate of our universe. The cosmic tug-of-war between the outward expansion of space, driven by dark energy, and the inward pull of gravity, dominated by dark matter, will determine the final chapter of our universe. Understanding dark matter is not just about understanding the past and the present, but also about predicting the very distant future. Let's return for a moment to the cosmic web. This structure is not static. It is constantly evolving, growing, and changing over billions of years. The filaments thicken as they draw in more matter. The clusters at the nodes grow larger and more massive as they accrete galaxies from the surrounding filaments. It is a slow, cosmic process of construction, with gravity as the builder and dark matter as the primary material. Our own Milky Way galaxy is currently traveling along one of these cosmic filaments on a collision course with our neighbor, the Andromeda Galaxy. In about 4.5 billion years, our two galaxies will merge. This grand, cosmic event will be orchestrated and guided by the immense dark matter halos that surround both galaxies. The halos will interact first, their gravitational fields mingling, pulling the two luminous spirals together into a single, much larger elliptical galaxy. This process is happening all over the universe. The cosmic web is the site of constant growth and galactic cannibalism, all driven by the relentless, invisible pull of dark matter. When we think of the void, the vast, empty spaces between the filaments, we often imagine them as true nothingness. But even these voids are not entirely empty. They are simply regions with a much lower density of both dark and ordinary matter. They're the great cosmic deserts, while the filaments are the fertile river valleys where life and structure can flourish. The contrast between the dense, galaxy-rich filaments and the stark emptiness of the voids is one of the most striking features of our universe, and it is a direct consequence of the behavior of dark matter. It is a substance that is inherently clumpy. It likes to gather together, and its gravity amplifies this tendency, pulling more and more matter into the same regions, leaving other areas depleted. This process, known as hierarchical structure formation, is a bottom-up construction of the universe. Small clumps of dark matter formed first in the early universe. These small halos then merged to form larger halos, which in turn merged to form even larger ones. The galaxies we see today are the luminous tips of these merged halos, the visible evidence of this long history of cosmic mergers and acquisitions. The search for dark matter is not just happening deep underground. It is also happening in space and with powerful particle accelerators. Some scientists hope to detect dark matter indirectly. The idea is that if dark matter particles are WIMPs, they should occasionally collide with their own antimatter counterparts and annihilate each other, producing a spray of familiar particles like gamma rays or neutrinos. Telescopes like the Fermi Gamma Ray Space Telescope scan the skies, looking for an excess of gamma rays. Coming from regions where dark matter is expected to be dense, such as the center of our own galaxy or in nearby dwarf galaxies, which are thought to be almost entirely dominated by dark matter. So far, no definitive signal has been found, but the search continues, refining its techniques and gathering more data. Another approach is to try to create dark matter particles here on Earth. At the Large Hadron Collider, or LHC, at CERN, physicists collide protons at nearly the speed of light. The goal is to recreate the energetic conditions of the very early universe. If the theories that predict WIMPs, like supersymmetry, are correct, these collisions could occasionally produce dark matter particles. We wouldn't be able to see the dark matter particles themselves in the detector because they are invisible and weakly interacting, but we could infer their presence. They would carry away energy and momentum from the collision, and this missing energy would be a telltale signature that something new and invisible has been created. Again, despite years of searching, the LHC has not yet found definitive evidence of dark matter production, which has led physicists to reconsider some of the simplest models of WIMPs and to explore other, more complex possibilities. The mystery of dark matter is a beautiful example of how science works. It is a puzzle with many pieces gathered from different fields: observational astronomy, theoretical physics, particle physics experiments, and cosmological simulations. All these pieces point towards the same conclusion. Our universe is dominated by an invisible form of matter. But the central piece of the puzzle, the identity of the particle itself, is still missing. This is what makes it one of the most compelling and urgent questions in all of science. It is a challenge that has spurred incredible innovation and creativity, pushing the boundaries of what we can measure and what we can imagine. Let's take a moment to visualize the scale we're talking about. The dark matter halo of our own Milky Way is thought to be about 10 times more massive than all the stars in our galaxy combined. It extends for hundreds of thousands of light years in all directions, a vast spherical cloud in which our spiral disk is just a small embedded feature. This means that as our solar system orbits the center of the galaxy, It is moving through a constant, though very thin, wind of dark matter particles. Billions of them are passing through your body every second without you ever noticing. They do not push, they do not pull, they do not interact. They are simply passing through, ghosts from a different sector of reality. Their presence felt only through the collective gravity of the trillions upon trillions of them that make up our galaxy's halo. This is a humbling thought. It connects us to the grandest scales of the cosmos in a very direct, physical way. We are not separate from this great mystery. We are immersed in it. The very atoms of our bodies are moving in a dance choreographed by an invisible partner. The stability of our sun's orbit, the existence of our planet, the long, quiet history of life on Earth, all of it is predicated on our galaxy being embedded in this massive, stabilizing cushion of dark matter. Without it, the galaxy might have been more chaotic, its structure less stable, perhaps making it a less hospitable place for life to emerge and thrive. So, in a very real sense, we owe our existence to this dark, mysterious substance. It is not something alien or foreign. It is a fundamental part of our cosmic environment, the bedrock upon which our home is built. As we continue our journey deeper into the night, let this thought bring a sense of peace and security. The universe is held together by a powerful, silent force. There is an underlying order, an invisible architecture that provides stability and structure to the cosmos. Even in the darkness, there is a design, a quiet, gravitational design that has been unfolding for over 13 billion years. And we are fortunate enough to be here, now, in a time when we're just beginning to perceive its faint outlines, to understand its profound importance. The story is far from over. The coming years promise new telescopes, more sensitive detectors, and more powerful simulations. Each will bring us a little closer to understanding the nature of the dark. And with each step, the map of our universe will become a little more complete, a little more detailed, a little more wondrous. The quiet architecture of the cosmos is slowly revealing itself to us, not in a flash of light, but in the patient accumulation of evidence, in the careful study of shadows, in the gentle pull of an unseen hand. Allow your mind to drift along these cosmic filaments, to rest in the deep gravity wells of the dark matter halos. Feel the immense stillness of the cosmic voids, the profound silence of intergalactic space. The universe is a vast and quiet place, and its grandest structures are built in that silence, shaped by a force that makes no sound and emits no light. It is a universe of subtle whispers and invisible influences, a place of deep and abiding mystery. And there is a profound comfort in that, a comfort in knowing that there is always more to learn, always more to explore, a comfort in being part of something so immense, so ancient, and so beautifully mysterious. Let this cosmic perspective soothe you, calm your mind, and guide you gently into a state of deep, restorative rest. The dance of the galaxies, the spinning of the stars, the slow, patient construction of the cosmic web. all of it continues, whether we are watching or not. It is the silent, constant music of the spheres, and its primary instrument is the gravity of dark matter. As you listen to the rhythm of your own breath, imagine it is in harmony with this silent, cosmic rhythm, a rhythm of expansion and collapse, of gravity and light, of the known and the unknown. You're a part of this rhythm. You are a small, luminous part of a vast, dark, and beautiful universe. And in this moment, all that is required is for you to rest, to let go, and to trust in the quiet, underlying order of things. The universe will continue its silent work, weaving its grand tapestry in the dark, and you can sleep peacefully within its immense and stable embrace. The nature of dark matter also presents a fascinating philosophical question. If the majority of matter in the universe is of a kind that does not interact with light, it implies that our perception of reality is incredibly limited. We have evolved to perceive the world through the electromagnetic spectrum, through light and sight. Our entire biological and technological sensorium is based on it. Yet, this is only a tiny sliver of what constitutes reality. It is as if we have been living in a house, exploring its brightly lit rooms, without ever realizing that the house itself is just one small part of a vast, unseen landscape. The existence of dark matter forces us to confront the limitations of our own senses and to appreciate that reality is far richer and more complex than our immediate experience suggests. It encourages a form of cosmic humility. The universe is not designed for our convenience or for the ease of our perception. It follows its own laws, and much of its substance lies beyond our direct grasp. We must learn to read its secrets indirectly, through the subtle language of gravitational effects, through the careful analysis of missing energy, through the patient search for a particle that is defined more by what it doesn't do than by what it does. This quest is a testament to the power of the human mind to transcend its biological limitations and to build a picture of reality based on reason, mathematics, and indirect evidence. It is a journey into a realm that we can never see, but that we can hope to understand. This invisible world of dark matter is not just out there in the cosmos. It is here now all around us. The particles that form this substance are flowing through the room you are in, passing through the very structure of your home, and through you as effortlessly as a thought. This constant, silent stream is a fundamental aspect of your environment, as real as the air you breathe, yet utterly imperceptible. Imagine trying to describe the concept of air to a creature that has no sense of touch or pressure. This is the challenge we face with dark matter. We are trying to characterize a substance whose primary characteristic is its profound aloofness from our world of ordinary matter. This is why the search is so difficult and why any potential discovery would be so revolutionary. It would not just add a new particle to our list. It would open a window into a hidden sector of the universe, a parallel world of particles and forces that coexist with our own, interacting only through the gentle, persistent whisper of gravity. Consider the dwarf spheroidal galaxies. These are small, faint satellite galaxies that orbit our own Milky Way. They are ancient, composed of old stars, and they are incredibly diffuse. But when we measure the motions of the stars within them, we find, yet again, that they are moving far too quickly. These tiny, ghost-like galaxies appear to be almost entirely made of dark matter. The stars within them are like a few scattered lights in a vast, invisible city. In some cases, the dark matter outweighs the ordinary matter by a factor of 100 to 1, or even more. These dwarf galaxies are therefore natural laboratories for studying dark matter. They are places where its effects are amplified and easier to observe, free from the complexities of a large, messy galaxy like our own. By studying these faint companions to the Milky Way, astronomers can map the distribution of dark matter on smaller scales, testing theories about its properties. Does it clump together as our models predict? Does it have any subtle interactions that we might be able to detect? These small galaxies hold important clues to the larger puzzle. The ongoing investigation into dark matter is also a story of scientific perseverance. Vera Rubin, for example, faced significant barriers as a woman in a male-dominated field, yet her meticulous work and unwavering focus on the data fundamentally changed our view of the cosmos. The thousands of scientists working on experiments like the LHC or the underground dark matter detectors are dedicating their careers to a search that may not yield results for decades. It is a long, patient game, driven by a deep sense of curiosity and the desire to understand our place in the universe. This collective human endeavor, spanning continents and generations, is in itself a beautiful thing. It is a quiet, collaborative effort to shine a light, however faint, into the deepest darkness we have ever encountered. And as you continue to relax, to let go of the day, allow your mind to appreciate this patient, persistent quality of discovery. The universe does not give up its secrets easily. It requires careful observation, clever experimentation, and the willingness to embrace ideas that seem strange or counterintuitive. The story of dark matter is a perfect example of this process. It began with a puzzling observation that was ignored for decades. It was revived by new data that was impossible to dismiss, and it has now grown into a global quest involving thousands of people, all working together to solve a single, profound mystery. This is how we learn. This is how we expand our understanding of the world, not through sudden, easy answers, but through the slow, steady accumulation of knowledge, through the courage to question our assumptions, and through the shared human drive to explore the unknown. Let this thought be a source of calm and reassurance. There is a process to understanding, a quiet and orderly path to knowledge. And as you sleep, that process continues. All over the world, telescopes are turning towards the night sky. Detectors are listening in the quiet depths of the earth, and theorists are scribbling equations on blackboards, all part of this grand, collective effort to map the invisible. You can rest knowing that the quest for knowledge is in good hands, that the journey into the dark continues, patiently and persistently on your behalf. The cosmos is a book filled with endless chapters, and we are just beginning to learn how to read its most subtle and mysterious language. The language of gravity, the language of the dark. And in that language is written the true story of how our universe came to be. So breathe deeply and let the vast, quiet, and stable architecture of the cosmos be the foundation for your own deep and peaceful rest. The invisible scaffolding holds the galaxies in place, a silent, powerful guardian of cosmic order. Allow that sense of profound stability and quiet strength to permeate your being as you drift effortlessly into sleep, secure in your small, luminous corner of a vast and wondrously dark universe. The very existence of dark matter also helps to solve another cosmological puzzle, the flatness of the universe. Observations of the cosmic microwave background have shown us that, on the largest scales, the geometry of space-time is remarkably flat. This means that if you were to draw a triangle with sides stretching for billions of light years, its angles would add up to 180 degrees, just as they do on a flat sheet of paper. According to Einstein's theory of general relativity, the geometry of a universe is determined by its total density of matter and energy. There is a specific value, known as the critical density, that would result in a perfectly flat universe. If the universe's density were less than this critical value, it would have a negative saddle-like curvature. If it were more, it would have a positive spherical curvature. When we add up all the visible matter and energy we can see, we get a value that is far too low. It's only about 5% of the critical density needed to make the universe flat. This was a major problem for cosmologists. But when we add in the contribution from dark matter, which we have inferred from its gravitational effects, we get much closer. Dark matter makes up about 27% of the critical density. When we also add in dark energy, a mysterious force causing the expansion of the universe to accelerate, which makes up the remaining 68%, we arrive at a total density that is almost exactly the critical density. The numbers match perfectly. The flatness of the universe, a measured and observed fact, is a powerful piece of corroborating evidence for the existence of both dark matter and dark energy. They are not just ad hoc additions to our model. They are necessary components to make the entire cosmological picture consistent. Each piece of evidence, from galaxy rotation to gravitational lensing, from the cosmic microwave background to the flatness of the universe, points to the same conclusion. They are all different threads that, when woven together, create a rich and coherent tapestry of a universe dominated by unseen substances. This convergence of evidence from completely different types of observations is what gives cosmologists such confidence that dark matter is real, even if we don't yet know what it is. It is not just one anomaly. It is a consistent pattern of anomalies that all disappear when we introduce this one new ingredient. This process is like a detective story. The detective finds muddy footprints of the crime scene, a missing item, a strange noise heard by a neighbor. Each clue on its own might be dismissed, but when all the clues point to a single, unseen suspect, the case becomes compelling. In cosmology, dark matter is that unseen suspect. Its gravitational footprints are all over the cosmos. And while we haven't caught it yet, the circumstantial evidence is overwhelming. Let's think about the different forms this dark matter could take. While WIMPs and axions are the most popular candidates, physicists have explored a whole zoo of other possibilities. Perhaps dark matter is not just one particle, but a whole dark sector of particles, with its own forces and interactions, a parallel universe of complexity that only interacts with us through the shared force of gravity. Perhaps dark matter has some form of self-interaction, meaning dark matter particles can collide and interact with each other, even if they don't interact with us. This could explain some subtle discrepancies in the observations of dark matter distribution on small galactic scales. Some theories propose the existence of sterile neutrinos, a fourth type of neutrino that is much heavier than the three known types and does not participate in the weak nuclear force. These could have been produced in the early universe and could account for the missing mass. Other, more exotic ideas suggest that dark matter is not a particle at all, but manifestation of a modification to the laws of gravity itself on large scales. These theories, known as modified Newtonian dynamics or MOND, are less popular because they struggle to explain the full range of observational evidence, particularly the patterns in the cosmic microwave background and the effects of gravitational lensing in colliding galaxy clusters. However, they serve as a valuable reminder that we must keep an open mind and test our fundamental assumptions. The wide range of possibilities shows how vibrant and active this field of research is. It is a mystery that has captured the imagination of a generation of physicists and astronomers, and they are exploring every conceivable avenue to solve it. This intellectual exploration, this journey into the unknown, is a deeply human activity. It is driven by the same curiosity that led our ancestors to look up at the stars and wonder about their nature. Today, we are still looking up at the stars, but we are also looking down into the depths of the earth and inward into the fundamental laws of particle physics, all in the service of answering this one profound question: what is the universe made of? As you lie here on the cusp of sleep, you are part of a planet that is hurtling through space at hundreds of kilometers per second, orbiting the center of a galaxy that is itself moving through the universe at even greater speeds. All of this motion, this grand cosmic dance, is being conducted by an invisible master. The stability of your journey through the cosmos is guaranteed by this unseen substance. There is a deep, rhythmic, and predictable order to these celestial motions, an order established by the gentle, persistent, and all-encompassing gravity of dark matter. Allow your own breathing to find a slow, deep, and predictable rhythm. Let the rise and fall of your chest mirror the slow, gravitational collapse of matter in the early universe, the patient gathering of material that would one day form stars, planets, and life. You are a product of this cosmic architecture, a small, intricate structure built from the ordinary matter that settled into the deep gravitational wells carved out by the dark. There is a connection between the grandest scales of the cosmos and the smallest scales of your own being. The elements in your body were forged in the hearts of stars, and those stars were gathered together by the gravity of dark matter. You are, in the most literal sense, a child of the cosmos, a child of both the light and the dark. Let this thought dissolve any remaining tension in your body and mind. Let it bring a sense of belonging, a sense of being part of something vast, ancient, and profoundly beautiful. The mystery of dark matter is not a source of anxiety, but a source of wonder. It is a gentle reminder that the universe is full of secrets, and that the process of discovery is a long and peaceful journey. And tonight, your journey is into the quiet, restorative darkness of sleep, a darkness that echoes the peaceful, creative darkness of the cosmos itself. Rest now, and let the silent music of the universe be your lullaby as your mind drifts on this cosmic tide. Let us listen more closely to this silent music. For though it is silent to our ears, it is not without its echoes. The universe is filled with the faint, resonant hum of dark matter's influence, whispers left behind in the motion of the stars and the bending of light itself. We have learned to hear these whispers, not with our ears, but with our telescopes, which are our windows into the deep past and the vast expanse. Imagine a grand, spinning pinwheel of light, a spiral galaxy suspended in the blackness of space. Billions of stars, like tiny embers, trace out its elegant arms. You might imagine that this cosmic pinwheel spins like our own solar system. The inner planets, like Mercury, race around the sun, while the distant planets, like Neptune, move at a much more leisurely pace, their orbits dictated by the sun's diminishing gravitational pull. For decades, we assumed galaxies behaved in the same way. We expected the stars on the far outer edges of the galactic disk to be moving slowly, barely held in the gravitational embrace of the galaxy's bright center. But when we carefully measured the speed of these distant, lonely stars, we found something astonishing, something that defied all expectations. They were moving far too fast. They were racing along in their orbits at speeds that should have flung them out into the lonely void between galaxies. The visible matter of the galaxy, all the stars, the gas, and the dust we could see, did not have nearly enough gravity to hold on to them. It was like watching children on a carousel spinning so fast they should be flying off, yet they remained perfectly in place. The only possible conclusion was that there was something else there, a vast, invisible halo of mass, extending far beyond the visible light of the galaxy, enshrouding it in a massive, unseen sphere. This halo, composed of dark matter, provides the extra gravitational grip, the unseen tether that holds these speeding stars in their orbits. This was one of the first and most powerful whispers from the dark, a clear indication that the universe we see is merely the luminous tip of a much larger, invisible iceberg. This unseen presence reveals itself in other, even more profound ways. Albert Einstein taught us that space and time are not fixed, empty stage upon which the universe performs. Instead, they form a dynamic, flexible fabric. Massive objects like stars and galaxies create deep divots in this fabric, much like a heavy ball placed on a stretched sheet. And just as a marble rolling across the sheet will have its path curved by the divot, so too is the path of light bent as it travels through the cosmos. This phenomenon, known as gravitational lensing, allows us to see the influence of mass we cannot see directly. Now, picture looking out into the deepest reaches of space. You're looking at light that has traveled for billions of years to reach you. On its long journey, that light has passed through and around immense clusters of galaxies, the largest known structures in the universe. As the light navigates the gravitational divots created by these clusters, its path is bent and distorted. When we observe the light from a very distant galaxy that lies behind one of these clusters, we see a strange and beautiful sight. The galaxy's image might be stretched into a long, thin arc of light. We might see multiple images of the same galaxy scattered around the cluster like reflections in a warped mirror. Here, again, the mystery deepens. When we measure the amount of distortion, the degree to which the light is bent, we can calculate how much mass must be in the intervening cluster to create such an effect. And time again, the result is the same. The visible matter, the hundreds or thousands of galaxies in the cluster, accounts for only a small fraction of the required mass. The vast majority of the gravity is coming from something else, something spread invisibly throughout the entire cluster. It is the dark matter, the invisible scaffolding itself, that is warping the fabric of space-time. We cannot see it, but we can see the universe bending around it. We are witnessing the silent design of the cosmos, sketched out in the distorted light of ancient galaxies. The darkness is not empty. It is full, heavy, and powerful, shaping the very light that travels through it. Let your mind rest on this thought. The thought of an invisible architecture so vast it uses entire galaxies as its tracers and beams of light as its measuring stick. And this invisible architecture does more than just bend light. It is the master blueprint for the placement of everything we can see. If we could zoom out far beyond our own Milky Way, beyond our local group of galaxies, and see the universe on the largest possible scale, we would not find a random scattering of stars and gas. Instead, we would see a structure of breathtaking complexity and order, a pattern known as the cosmic web. Imagine a vast, three-dimensional network stretching across billions of light years. It is made of long, delicate filaments of galaxies, flowing like cosmic rivers through the darkness. Where these filaments intersect, they form dense, bright knots, the great galaxy clusters, cities of light teeming with thousands of galaxies. And in between this luminous network lie the great cosmic voids, immense regions of profound emptiness, hundreds of millions of light years across, where galaxies are few and far between. This grand structure, this cosmic web, is the most direct and stunning manifestation of the dark matter scaffolding. For billions of years, gravity has been patiently at work, pulling matter together. But the gravity of ordinary matter alone, the stars, the gas, the dust, is simply not enough to have created this intricate pattern in the age of the universe. The expansion of space that began with the Big Bang was a powerful outward force, working to pull everything apart. For matter to clump together into the filaments and clusters we see today, it needed an extra gravitational pull, a head start. Dark matter provided that head start. Because it does not interact with light or radiation, it was not pushed around by the energetic photons that filled the early universe. It was free to begin collapsing under its own gravity, forming deep, invisible pools and channels of mass. Ordinary matter, the stuff we're made of, then fell into these pre-existing gravitational valleys like water settling into the contours of a landscape. The galaxies we see today are merely the luminous foam on the unseen currents of dark matter that dictated their final resting place. We can test this idea with startling accuracy. Using our most powerful supercomputers, we can create virtual universes. We program in the fundamental laws of physics, gravity, expansion, and we add the ingredients that we believe make up our cosmos. A little bit of ordinary matter, a healthy dose of dark matter, and a mysterious dark energy that drives cosmic acceleration. We then press play and watch as 13.8 billion years of cosmic evolution unfold in a matter of weeks. What emerges from these simulations is not a guess, but a direct calculation. And the result is a stunningly beautiful, intricate web-like structure that looks identical to the one we observe in the real universe through our telescopes. If we run the simulation without dark matter, the universe remains too smooth, too uniform. No web forms. The galaxies are left adrift. It is only when we add this vast, unseen component that the silent design of the cosmos snaps into focus. But where did the initial seeds for this structure come from? To find the answer, we must travel back in time, almost to the very beginning. We look not at galaxies, but at the oldest light in the universe, the faint afterglow of the Big Bang itself. This light, called the cosmic microwave background, or CMB, comes to us from every direction in the sky. It is a snapshot of the universe when it was a mere 380,000 years old, hot, dense, and nearly uniform plasma. Nearly uniform, but not perfectly. Embedded in this ancient light are tiny, almost imperceptible variations in temperature, spots that are a few millionths of a degree warmer or cooler than the average. These tiny fluctuations were the primordial seeds, the initial density variations from which all future structure, including our own galaxy, would eventually grow. Here, in this baby picture of the universe, we find one of the most powerful clues to the nature of dark matter. In the primordial soup of the early cosmos, two great forces were at play: the inward pull of gravity and the outward push of radiation pressure. Ordinary matter, being made of charged particles, was tightly coupled to the light, the photons. It was caught in a cosmic tug-of-war, compressing in the slightly denser regions due to gravity, then bouncing back out as the pressure from the trapped light became too great. This created ripples like sound waves sloshing through the plasma. But dark matter, being invisible to light, felt no radiation pressure. It felt only the gentle, persistent pull of gravity. So while ordinary matter was oscillating in and out, the dark matter could steadily begin to pool in the denser regions, deepening the gravitational wells. This fundamental difference in behavior left a distinct signature in the pattern of the hot and cold spots in the cosmic microwave background. The precise size and distribution of these spots are a direct record of that ancient interplay. When we measure that pattern, we're reading a recipe for the universe, and that recipe is unequivocal. To create the specific pattern of ripples we see, the universe must contain roughly 5 times more dark matter than ordinary matter. The blueprint for the invisible scaffolding was there, imprinted on the very first light of creation.